Ahoy, students! Now that we've had a look at exponential equations, it's time to look at logarithmic equations. A logarithmic equation is just an equation where a variable occurs inside of a logarithm. For example, we can look at log base 3 of x minus 4 equals 2. When we have a logarithmic equation where we have a variable inside a logarithm and we want to isolate the variable, to solve for the variable, everything is easier when we rewrite it in exponential form. So if we were to rewrite this in exponential form, we would have 3 as the base, 2 would be the exponent, and this is equal to x minus 4. Again, remember, we can write any logarithmic equation as an exponential equation as well, just by rearranging the bits. And so when we write this as an exponential equation, it becomes basically simple to solve. 3 squared is 9, and so we've got 9 equals x minus 4, and this is a basic linear equation. To get x alone, we add 4 to both sides, and we get our solution of 13 equals x. So basically, anytime we have a logarithmic equation, we can make it simpler by writing it as an exponential equation. Let's take a look at another example. We've got ln of x equals 8. If we rewrite this as an exponential equation, it becomes e to the 8th equals x. And that is our solution. If we want an approximation, of course, we can use a calculator, but I'm going to leave it like this for now. Let's do another one. Let's look at 4 plus 3 log of 2x equals 16. Now here, before we can write anything in exponential form, we need to isolate the logarithm by itself. So to do that, we're going to subtract 4 from both sides, leaving us with 3 log of 2x equals 12. Then we can divide both sides by 3, giving us log of 2x equals 4. And then we can rewrite this in exponential form. This is a common logarithm, so the base is 10. So we've got 10 to the 4th equals 2x. 10 to the 4th is 10,000. So we've got 10,000 equals 2x. And if we divide by 2, we get x equals 5,000. So here we had to isolate the logarithm first before we converted it to exponential form, but we were able to do this nevertheless. Let's take a look at one more example. Let's take a look at log of x plus 2 plus log of x minus 1 equals 1. Now here we have two different logarithms. If we want to be able to write this in exponential form, we need to combine them. But we can do that by recognizing that the sum of two logarithms is equal to the logarithm of the product of those quantities. So this becomes the logarithm of x plus 2 times x minus 1. Now, when we write this in exponential form, it becomes 10, which is the base, to the first power equals x plus 2 times x minus 1. Now, if we want to solve this equation, we're actually going to have to expand this out and get all of the terms on the same side, because for a quadratic equation to solve, we need one side to be equal to 0. So first, 10 to the first is just 10. Now on the right-hand side, we can FOIL this out. X squared minus x plus 2x minus 2. When we combine like terms, this becomes x squared plus x minus 2, and that's equal to 10. And then we can subtract 10 from both sides. This gives us 0 equals x squared plus x minus 12. Now, to factor this, we can try the unfoiling method. We need two numbers that have a product of negative 12 and a sum of 1. Those numbers are positive 4 and negative 3. And if we set each of these factors equal to 0, we end up with x equals negative 4 or x equals 3. But there is one thing that we have to check in this situation, and that is we need to make sure that these numbers make the logarithms defined. Now here's a problem. If we try and use negative 4 as a solution, then when we plug it in, negative 4 minus 2 is negative 2, and we've got log of negative 2, which is undefined. So x equals negative 4 is actually not a solution. It is an extraneous solution. And we have to be careful because we are likely to get extraneous solutions when we take two logarithms and combine them into one, because it's possible that we've got negative numbers in each of these, and a negative times a negative gives us a positive. So it might work when we combine the logarithms, but in the original equation, we'll have logarithms of negatives which are undefined and which don't work. So we do need to make sure that whatever solutions we end up with in the end fit in the domains of the original logarithmic functions that we started with. In this case, if we try to plug in x equals 3 to each of these, we will end up with positive numbers inside the logarithms. So this is a real solution, and in fact, the only solution to this equation.